Welcome back, chemistry fans. Today, what we've got on tap for you is topic number 7, but this time it's topic 3. We're going to try and fix a few details. They're just minor little stories that need to be cobbled together, seemingly unrelated, but they all make for a bigger picture talking about bond energy. Let's jump into it. And let me share my screen with you here. Last class, we talked about, this is topic 4. Last class, we talked about lattice energy. Now, lattice energy involves a series of reactions that you had to convert into these formulas, into their symbols. Well, you were given these heats of the reaction for each one of them. The problem is we don't know where those came from. And so that's what we're going to try and deal with to start in this next topic. We are going to start with something called bond energy. So let's jump into bond energy. It is the amount of energy released whenever we have atoms that are broken apart. Now, the same energy, just like it was in lattice energy, can be for the reverse. Whenever we bring those two atoms together, it's the same amount of energy. It's just in the opposite. If it takes energy to break them apart, it's going to release energy when they come back together. So these energies work both ways. Amount of energy required to break a bond. So we are going to take these H2s and turn them into 2 different H's. Now, this stability can be mapped on a chart that you might see at some point. I want you to be familiar with it. It's inversely related to what you would think, however, though. So as we see in this, the amount of energy is close to neutral because they're too far away. So it doesn't take any energy for us to break these 2 atoms apart when they're too far apart. However, it is going to require us some energy whenever they are bonded together. And if they are too close, we have to add a lot of energy. And so that's what these charts are trying to seemingly show to you. Now, what we can see in these charts is the fact that the strength of the bonds increases with the number of bonds that are in them. Their length also is inversely related in that it decreases. So notice, if I have a triple bond, the amount of energy is increasing, but the distance is decreasing. So those are 2 important relationships that we need to be able to investigate. Here is a problem dealing with these bond energies. It's a fairly simple concept. What we have to know, though, is the overarching principle that to solve this mathematically, it's products minus reactants. So what we're going to do is we're going to look on this table and find the HCl. It says that it requires 427 kilojoules per mole. There are 2 moles in this reaction. So it's going to be 2 times 427 minus, now we've got the heat that is going to be necessary to break apart the hydrogens and the chlorines. So the hydrogens, 432 minus 432. I don't need to multiply it by 2 because it's already got the 2 H's, and minus 239 for the chlorines. So we're simply going to add all those values together, subtract them where necessary. So 427 plus 427 minus 432 minus 239. To make this molecule, these 2 molecules of HCl, it's going to require that I add 138 kilojoules of heat. That's how we calculate this. All right, another seemingly unrelated topic are bond angles. So again, not something that you need to memorize yet, but this portion of the table right here is what you would be expected to know. You need to know that linears have an angle of 180. Now, how do we come up with that? Well, we should know at this point from our mathematics world that a circle has 360 degrees. If we were to cut that in half, that's where we get the 180. If we were to take 360 and we were to divide that by 3, which is the case for the trigonal planar, that's where we get the 120. Now, here's where it gets weird, though. If you take that same 360 and you divide it by 4, you should get 90. However, it's a little bit off. It's 109.5, and that's just slightly increased over the 90 that we thought. So that's for the trigonal pyramid, that's for the tetrahedral. And then what we have on the expanded octets, we have this triangle in the middle, and it has 120, but then on the ones going up and down, they're 90 degrees. It's a little bit easier. For the octahedral, all of the angles are 90 degrees in that one. So once we establish what the shape is, we can determine what the angle is between them. All right, now another way in which we can categorize our bonds is by counting their bond order. Bond order simply is the number of bonds. It's that simple. If we have a triple bond, we have a bond order of 3. If we have a double bond, we have a bond order of 2. If we have a single bond, it's a bond order of 1. If, however, we have this scenario developing where we have multiple bonds on the same molecule, or we have them split where we have a single and a double, we take the average of both of them. So we would have a total of 1 plus 2 divided by 2 locations. So that means that the bond order in this case would be 1.5. On the right side, we have 2 plus 1 plus 1 divided by 3 different locations. And so that would be 4/3. So that would be 1.3 would be our bond order. Okay. Speaking of dividing those into little different sections. Oh, here's another example of what that's showing you with the bond orders being smaller. Let's practice on this one here. So what would be the bond order of this molecule? So what we would have in this scenario is 1, 2, and then another 2 order for that bottom one, but we need to divide it by the 3 different locations. And again, this is where we get 4/3, which is equal to 1.33 is the overall bond order for this molecule. All right, let's jump into hybridization now. Hybridization, topic 5. We will talk and pick that up here in just a second. Thank you very much for getting into that first topic. We will pick it up with hybridization in just a second. Bye-bye.